Hello students, welcome you all. In NMR spectroscopy, today I will explain about the shielding and deshielding concept and chemical shift. Now, so what do you mean by the shielding and deshielding? We know that if we want to take the NMR spectra of any sample, then first of all, the sample is kept in between the strong magnetic field, external magnetic field. Now, so suppose if we have a sample and this sample may have a different kinds of proton in which they may have, and each kind of proton will give a signal. Okay, if there are 3 kind of proton, we will have a 3 signal. If we have a 10 type of proton, we will have a 10 type of signals. Now, so suppose if we have a proton, so this is a proton, and these protons, we know that these are surrounded by the electron cloud, or we can say this is the electron density surrounding the proton, and each proton will have the different electron density surrounding it, because each proton has the different environment. Some of the proton may have one of the electron withdrawing group. Some of the proton may have an electron releasing group in its neighbor. So that's why each proton has the different environment of the surrounding electron. Okay, so these electrons, we know that these electrons are revolving. These electrons are revolving around the proton, and due to this circulating electron, they produce a local diamagnetic current, which is called as the LDC. So circulating electrons, these are the circulating electrons. Produce LDC, that is local diamagnetic current. Okay. Now, so this local diamagnetic current, which this current, if there, then it produces a magnetic field also. So this local diamagnetic current, circulating current, it produces its own magnetic field, which is also called as the induced magnetic field. So due to this, it will produce its own magnetic field like this. It will produce its own magnetic field in this direction. And to record the NMR spectra of this molecule containing this proton, external magnetic field, suppose B0, is applied, and this induced magnetic field, so this is the external magnetic field, and this circulating electron, they will produce a induced magnetic field. And you can see this induced magnetic field here, this is in the opposite direction. It is in the opposite direction to the external magnetic field. Okay. So so this induced magnetic field, BI is the, suppose BI is induced magnetic field, and it is also called as the secondary magnetic field. Secondary magnetic field. Whereas this B0, this is the external magnetic field. Okay, so this due to this proton is shielded by these electrons, we can say, and these shielded electrons these shielded circulating electrons, they will produce a induced magnetic field which is in opposite direction to the external magnetic field. Okay, so these circulating electron produce LDC, local dynamic current, and this LDC generates induced magnetic field BI, and this, which is opposite to external magnetic field. Okay, so this induced magnetic field is opposite to the external magnetic field, and this is called as this is called as the diamagnetic shielding. Diamagnetic shielding. And why it is called as a diamagnetic shielding? Because this induced magnetic field is in opposite direction. Both have the opposite direction. If, for example, if two spins are in opposite direction, it means they are diamagnetic. If they are in parallel, then it is called as the paramagnetic. So this is called a diamagnetic shielding, or it is also called as a diamagnetic anisotropy. So why diamagnetic anisotropy? Because sometimes this induced magnetic field, this is not uniform in all directions. Somewhere it may have, this induced magnetic field may have a completely opposite to each other. Sometimes it is not so much opposite to the external magnetic field, or sometimes it may go parallel to the magnetic field here. For example, suppose a proton, somewhere the proton is in this direction, then here you can see this induced magnetic field is in parallel to the external magnetic field, whereas if proton are present here in this direction, they are opposite to the this external magnetic field. So this anisotropy, because when this shielding is not uniform, everywhere in a molecule, in one of the molecule, then that's why it is called, as it is not uniform, that's why it is called as the diamagnetic anisotropy. Okay, so suppose if we have a electron density, so if electron density surrounding the proton increases, or we can say, or if shielding increases, if electron density increases, then shielding, that will increase, and if the shielding increase, then this BI, that will also, that is induced magnetic field, will also increase. So if electron density is increasing, then what will happen? This frequency, operating frequency, which is falling over the proton, it will feel less frequency. So that's why, as it feels the less frequency, that's why it will resonate at a lower frequency. So resonating frequency, that is the precisional frequency, that will be the less. So frequency by which it resonates, that is a precisional frequency. Suppose I write it by omega. So precisional frequency by which the proton presses, that will decrease. So if precisional frequency decrease, it means suppose if we have this is scale, and this is the TMS scale, and this is the TMS scale, and suppose this is 0, this is 1, 2, 3, 4, 5, 6, 7, and so on. So what will happen? Suppose if we have a high electron density, then we will get the signal at lower frequency. So signal, this is taken in terms of a chemical shift that I will discuss later on. So this chemical shift in terms of ppm, which is directly proportional to this precessional frequency. This chemical shift is directly proportional to this frequency, precessional frequency, and we can convert this precessional frequency in terms of a chemical shift that I will tell you. So this means as the electron density increase, means if shielding increase, suppose if shielding increase, then this delta value which is proportional to this precessional frequency, that will also decrease. So if shielding increase, then delta value will decrease, and if shielding decrease, it means if we have a less electron density surrounding the proton, if shielding decrease, then delta value will increase. So this side, this right corner, this is called as the shielded region. So this is called as the shielded region. This is called as the shielded region, and this region, this is called the deshielded region. Deshielded region. So shielded region, this region is also called as the upfield. This is also called as the upfield. This is called upfield. Why? Because here the electron density, they are the induced field, they are producing more induced field. That's why it is called as the upfield, and this is called as the downfield. Signal at this side is called as the down. It is called as the downfield. Okay, so this is about the concept of shielding and deshielding. Means the circulating electrons surrounding the proton, they will produce a local diamagnetic current, and this current in turn, it will generate a induced magnetic field which is in opposite direction to the external magnetic field, and this is called as the diamagnetic shielding or diamagnetic anisotropy. Why it is called as the anisotropy? Because this diamagnetic shielding is not uniform all over the molecule. That's why this is called as the anisotropy. Now let us come to the concept of a chemical shift. Now come to this chemical shift. So what I told you, we record the NMR spectra on delta scale. Suppose this is a TMS, which is the signal at the right corner, and it is taken as a 0 reference. We may also have a signal at a minus also. So suppose this is 0, 1, 2, 3, 4, and so on. And like this. Okay, so this scale is in terms of delta, which is in ppm. Though the proton absorbs the frequency and the signals comes at a particular frequency, but that frequency, that can be the whole spectrophotometer which is connected to the computer, that will convert this frequency in terms of the delta value, and this delta is called as the chemical shift. So how can we define this chemical shift? What I told you, actually all the signals which are coming over here, suppose proton, one of the molecule is having 10 different types of proton. So we will have 10 different signals, and one of the signal that sometimes it gets split into 3 signals, or we can say it can be split into 3 peaks, or which is also called the peaklet. Okay, which is also called as a peaklet. So one signal can be split into 3, it may be split into 4, and many multiplet may be there. So that's why, and difference between the frequency of these peaks are quite small, and it is very difficult to distinguish the frequencies of these peaklets, these peaks. So that's why we record the frequency of all signals in terms of TMS. Or we can say that what is this chemical shift? Chemical shift is how far a signal is from TMS. Suppose if we are getting here, this one of the signal we are getting here. Okay, we are getting this signal and another signal we are getting here. So how far this signal is from TMS. So we can define this chemical shift is how far is the each signal each signal of proton is from the reference TMS. So this is the chemical shift. So we can what I told you, because this signal comes in terms of frequency, and the frequency is then converted into the delta value. So this chemical shift, the frequency that can be converted into the chemical shift. So this chemical shift, that is delta, this is equal to shift from TMS, in terms of hertz. This is the frequency of, this is the precessional frequency. This shift is this is the precessional frequency of the proton. This is the precessional frequency of the another proton. So shift with respect to TMS in hertz divided by spectrophotometer frequency. So this spectrophotometer frequency is very large and it is in terms of megahertz. So chemical shift, how this computer will convert this frequency of precessional frequency of the proton in terms of this delta value by dividing it by the spectrophotometer frequency, which is very high. It may be 300, 400, 500 and 600, as I told in my previous lecture, that if more is the spectrophotometer frequency, better will be the resolution. And nowadays we use the spectrophotometer which is having very high frequency, like it may be 600, 700 like this. And now to convert this, because to convert it to the same unit, we multiply it by 10 to the power 6. So this is also in megahertz, this is also in megahertz. So like this. So, but the delta value, if we change the operating frequency, that is spectrophotometer frequency, then in that case the frequency of the precessional frequency of proton, that will also increase, no doubt. So what I am saying, that if we increase the spectrophotometer frequency, then precessional frequency of the proton, this shift will also increase. But if we take the spectra in any spectrophotometer, whether the spectrophotometer is of 200 megahertz, it is of 400 megahertz, or it is of 600 megahertz, the delta value, the signal will come at the same place. Okay, so why? So because we can see here with the help of example. Suppose a spectrophotometer frequency, that is if we say that this is the operating frequency. So if operating frequency, suppose this operating frequency, if it is suppose 162 megahertz, and precessional frequency of the proton, suppose this is omega, which is the precessional frequency of the proton. So if precessional frequency of the proton is suppose 60 megahertz, 60 hertz, okay, then if we find the chemical shift, then chemical shift is equal to 1, it is equal to, suppose, sorry, if this is 162, if this is 162 hertz and this is 60 megahertz, it is 60 megahertz, then this is equal to 162 divided by 60, and this comes out to be around 2.7. This comes out to be 2.7, okay, into this by multiplying it by 10 to the power 6, we get 2.7 ppm. Okay, now this is the first case. Now suppose if we change the spectrophotometer frequency. Now second case, suppose spectrophotometer frequency, that is operating frequency, if this is equal to, suppose it is equal to 270 megahertz. It is 270 megahertz. Okay, and suppose in that case the precisional frequency, it comes out to be suppose 100 megahertz, 100 hertz. So what would be the delta value in this case? The delta value, this is equal to this, again I have written opposite that one. Suppose this is omega, that is the precisional frequency, and this is our operating frequency. I have written reverse. Now, so this is now correct. So in this case, the delta, this is equal to operating frequency, that is omega 270 hertz, and this is megahertz. Sorry, this is megahertz. The same way, here this is in megahertz, this is in hertz. So 270 divided by 100, and it comes out to be. So delta value remains same irrespective of spectrophotometer frequency. If we change the spectrophotometer frequency, then also the delta value, means the resonating frequency, the overall the delta value for the proton in a molecule, that remains same. If we take a spectra from any equipment, irrespective of its frequency, the delta value will remain the same. So this is about the chemical shift. Now in my next lecture, I will discuss about the factors affecting the chemical shift. Thank you.